We are talking about order of an element in a group. Let me remind you of the definition. G is a group. You fix an element A in G. Then first of all, you define powers of A. A to the 0 means the identity element E. A to the 1 means A. Excuse me. A square means A times A. A cube means A square times A, etc. That defines the positive powers. And then A to the minus 5 means A to the 5 inverse. A to the minus 6 means A to the 6 inverse, etc. So that defines A to the n for every integer n. And then you verify the usual exponential laws. A to the m times A to the n is A to the m plus n, and A to the m to the n is A to the mn for all mn. So in particular, A to the m inverse is A to the minus m for all m. An element A in a group G is said to have finite order if some positive power of it gives you identity. In other words, you say it has infinite order. So for example, in any finite group, you can see rather easily, if G is finite, then every element of G has finite order. In fact, we'll see that the order of the element divides the order of the group, the size of the group. I mean, that's just because you take, let's say G has 50 things in it. You take some A in G and you start writing the powers, identity A square, A cube, etc. By the time you get to A to the 49, you have already got 50 symbols. And now you get to A to the 50, here are 51 different things. G only has 50 things in it. So these 51 things cannot all be different. So two different ones got to be the same. And as soon as you get A to the I equals A to the j for some j bigger than I, you can cancel enough things, and that would tell you A to the j minus I is identity. That would show you that it has finite order. You can make a more refined statement later. So for example, S10, permutations of 10 letters. Remember, this is all permutations. This is an important group. Sn, this is permutations of 1 to n, 10. These are all one-to-one and on-to functions from 1, 2, 3, 4 up to 10 to 1, 2, 3, 4 up to 10. How many such functions are there? Well, there are 10 factorial, 1 times 2 times 3 times 4 times up to 10, that many functions. It's a fairly big group, but it's a finite group. So every element there is going to have finite order. If you say that something has finite order, let's define what its order means. The order of A, denoted by absolute value of A, means the smallest positive number when the nth power, smallest positive number n, such that the nth power of A is the identity element. Yeah. So if it has finite order, if you start taking the powers, at some point it comes down to identity, comes back to identity again. So it has to come back to identity for the first time at some stage, and that stage is called the order of the element. So we did some example, like this element of S4 had order 3, because it was switching 1 to 4 in a cyclic manner and fixing 3. So if you did it 3 times, everything came back to itself, so you got the identity. Let's see how to calculate order of an element in permutation group in general. So here is a more complicated element of permutation group. This is a permutation of 10 letters. So it's a function from 1, 2, 3, 4 up to 10 to 1, 2, 3, 4 up to 10. This is the function that takes 1 to 4, the function that takes 2 to 2, 10 to 3. We have a shorthand for that thing. It's written like this. We write 1, 2, 3, 4 up to 10, and then we say 1 goes to 4, 2 goes to 2, 3 goes to 9, etc. Okay? And I want to know how many times do I have to apply this function back to back when the result is that every number gets back to where it started from. So to do this, it's convenient to write this permutation in a shorter form. So I'll use this as an excuse to introduce what is called the cycle notation. And this has other uses too for permutation. And it's easiest to explain in an example. What you do is you basically start with 1 and track what happens. So let's start with 1. The first thing that is available is 1, the smallest number. And let's track what happens when I apply 1. 1 goes to 4. I write 4. And then I track what happens to 4. 4 goes to 6. And then, actually, let's track in a picture, like we did last time, So 1 goes to 4, and then 4 goes to 6, and then 6, look, comes back to 1. So 1, 4, and 6 are taken care of. Next, I go to the first thing that is available, which is 2. What happens to 2? Well, 2 stays at 2. Next, I go to the next thing available, 3. 3 goes to 9, and then 9 goes to 5, and then 5 goes to 10, and then 10 goes back to 3. And then what's the next thing that is available? 7. 7 or 8 are getting switched. So this is a more convenient picture of the permutation in some sense. Tells you how it moves things around with less writing. And you write this in a more compact form like this. So you write 1, 4, 6, and you close the parenthesis. 2 stays at 2. And then you take the next smallest one. So every time I'm taking the smallest one that is available, 3. And then I track that. 9 goes to 5, goes to 10, back to 3. And then 7 goes to 8, goes back to 7. And then sometimes you don't even write the single ones, because if you omit something, that means that that guy just got fixed. 2 just went to 2. So this now is going to be the cycle notation for F. A permutation that looks like this. So 3, 9, 5, 10. That is called a 4 cycle, because it just moves 4 things in a cycle. This is a 3 cycle. This is a 4 cycle. This is a 2 cycle. And F, you realize, is actually a product of these cycles in the permutation group. So we write, so this is F written as a disjoint product of cycles. We'll write down the definition more carefully, but the example tells you exactly. I think the word disjoint means that you see the numbers that appear in this cycle and the numbers that appear in this cycle are all distinct. Yeah. So what that actually tells you that the ordering is irrelevant. You could apply this cycle first, and then you could apply the 4 cycle first, and then apply the 3 cycle. It would give you exactly the same thing. At any rate, this is the cycle notation, and if you know the cycle notation, you can work out the order rather easily. You see, these 3 things, 1, 4, and 6, get permuted cyclically, whereas these 4 things, 3, 9, 5, and 10, get permuted cyclically. So if you do it after 3 times, 1, 4, and 6 has come back to their original position after every 3 times. Whereas 3, 9, 5, and 10 would come back to their original position after every 4 times. And 7 and 8 would come back to their original position every couple of times, every even number of times. So how many times do I have to apply F so that everything comes back? Well, that would be the LCM of the cycle lengths. In this case, 12 times. So you can check that the order of F is the L least common multiple of the cycle lengths in the cycle decomposition of F. So that's actually tells you how to calculate order of an element in the permutation group in general. Maybe we should do a little lemma about calculating orders of elements. A little lemma here that actually has some content. Take an element that has order n. And let t be a non-zero integer. Then I want to ask, what is the order of t? Sorry, what is the order of a to the power t? So I know the order of a. What's the order of some power of a? And the answer, let's guess the answer. So here is maybe some a. Let's put some face on these letters. Let's say a has order 20, which means a. If you start calculating a square, etc., a to the 20 is the first time it comes back to identity. Okay. And then I'm asking, let's say, what is the order of a to the 12? So t is 12, n is 20. So I give you a to the 12, and what I'm asking you is, what's the smallest power you can raise it to so that you get identity? And if you look at this, you can see a to the 12 to the power something, right? So I want some k so that a to the 12k is identity, and I want k to be as small as possible. So this 12k, if a to the 20 is e, then a to the 40 is e, and a to the 60 is e, and so on. And we know that these are the only positive powers for which you get the identity. We actually did that exercise last time. So 12k has to be one of these. So what's the smallest k such that 12k is one of these numbers? Well, 5 when you get 60. Right. So a to the 12 times 5 is e, which means a to the 12 to the 5 is e. So fifth power of this element, a to the 12, is already identity. Right? And you can check rather easily that no smaller power would work, because you at least want this number to be a multiple of 20, and this first time that happens is this at 60. So the order happens to be, in this case, 5. And how did you get this 5? If you think about this a little bit, the 5 is really 20 divided by 4, and this 4 is really the GCD of 20 and 12. That's the genesis of this 5, if you unpack what is going on. Because you wanted this number to be so that this product is a multiple of 20. And this is the smallest number for which 12 times a number is going to be a multiple of 20. Because the 4 is already in there, so you at least need a 5. So the answer is, this is n divided by GCD of n and t. Okay. Maybe we'll prove it next time.